Hi everyone, let's talk about the surface area and volume of a regular tetrahedron. A regular tetrahedron looks like this. We've got four triangles that come together into one shape like this, one polyhedron, and they're four equilateral triangles. And there's a unique such shape that fits together the four triangles in that way. Now, to analyze this, we're gonna first I'm gonna first tell you the results and then we'll look into the details. So the first thing is the surface area. That's equal to square root of 3s squared, where s is the side length of each of the triangles, and the volume is equal to square root of 2s cubed over 12. Now, to derive these, we're going to need to analyze the anatomy of an equilateral triangle, because that's what the shape or polyhedron, regular tetrahedron, is made up of. The first thing is its height, because we're going to end up needing its area, and for that we need the height. So let's split it up into two lengths, s over 2 and s over 2, and have an h here, and we have an s over here. That means by the Pythagorean theorem, h is equal to s squared minus s over 2 squared, square root over the whole thing, and that is equal to square root of 3s over 2. So that allows us to compute the area. The area, let's call it delta, is equal to sh over 2, and that is equal to s times square root of 3s over 2 over 2, and that is equal to square root of 3s squared over 4. So to find the surface area, we just multiply it by 4. So surface area is equal to 4 times delta, and that's just equal to square root of 3s squared. So we found the surface area. The volume is a bit more difficult because we have to find the height of the pyramid. So let's draw the pyramid again. And the height will be like this. Now we need to figure out what the height is, and we're going to use the Pythagorean theorem to do that. Our method will be to draw the in radius of the bottom triangle and use the Pythagorean theorem on it. So let's analyze what the in radius is for an equilateral triangle. Let's say this is the center of the equilateral triangle, then the in radius is each of these segments. Let's call the length small r. And it's well known that if the semi-perimeter is, let's say, well, in this case the semi-perimeter is just s plus s plus s over 2, which is 3s over 2. And what we know is that r times the semi-perimeter, which is 3s over 2, is equal to the area of the equilateral triangle. And you can figure that out by splitting the triangle up like this into three triangles, the three pink triangles. So this formula tells us that r times 3s over 2 is equal to square root of 3s squared over 4, and that in turn tells us that r is equal to square root of 3s over 6. So you can do that computation. It's just this part divided by this part. So now we know what r is, and what that lets us do is use the Pythagorean theorem on this pink triangle here. So let me draw out this pink triangle. What we know is that down here we have r, up here we have the height, let's call it h naught, of the pyramid, And here we have height of the equilateral triangle. So r is equal to square root of 3s over 6. And looking behind at what we did before, we know that the height of the equilateral triangle is square root of 3s over 2. So that's square root of 3s over 2. And now we can use the Pythagorean theorem. By Pythagorean theorem, h naught is equal to square root of 3s over 2 squared minus the in radius squared, which is square root of 3s over 6 squared, and square root over the whole thing. And if you simplify it, I'm not going to show the steps because it's some fairly straightforward algebra. But if you do the algebra, you find that it's equal to square root of 2 over square root of 3 times s. So that's the height of the pyramid, this height over here, which is also this height over here. So what that allows us to do is find the volume of the pyramid, because the volume is equal to 1/3 of the area of a base times the height of the pyramid. And that's something you need a bit of integration to prove in general for pyramids. So we're not going to prove that, but we're going to use this formula to get that it's equal to 1/3 times the area of a base, which is an equilateral triangle. And we have that over here. So square root of 3s squared over 4. Square root of 3s squared over 4 times the height, which is square root of 2 over square root of 3s. And now we get some cancellations because the two square root of 3's cancel out. And what we're left with is square root of 2s cubed over 12. And that's what we originally predicted the volume would be, square root of 2s cubed over 12. And that's our final formula for the volume. Thank you for watching, and I'll see you next time.